Hello, everybody.
Hello.
Hello.
Got a few people coming in here. Okay. Everybody can hear me okay? Everybody can see the screen, lecture 13?
Yes.
Yeah.
Okay, perfect. All righty. So we are going to talk tonight about statically indeterminate torsionally loaded members. That's kind of a mouthful. Check here real quick. I believe we are. Okay, we are now in section 5.5. And yeah, I think this is going to be, well, yeah. So we're going to talk about section 5.5, and then we're going to touch back on the power section, which was 5.3, I believe. Yeah, okay. Alrighty, so let's get started. So what we're talking about is some kind of a shaft or torsionally loaded member that is supported between two supports or wedged between two walls, basically. Here we have two unknowns. We have a reaction at A and reaction at C, and only one equation in order to sum our torques. This probably looks like deja vu. This probably looks somewhat familiar because this is pretty much the same setup as we did for statically indeterminate axially loaded members. Same idea. So summing the forces are trivial and lead only to a zero force. So summing the forces in the X, summing forces in the Y doesn't get you anywhere. We have to derive a second equation by comparing the relative rigidities of the two segments AB and BC. Here, we will present two methods to find the unknown reactions, namely the compatibility method and the flexibility method. Am I getting any deja vu here? It's really the same procedure as we use for axially loaded members. We'll start by exploring an example. So here I've got a rod A, B, C. Anytime you see a double-headed vector like this, that represents a torque or moment, and the direction of that torque is following the right-hand rule. So if you line up your thumb with the direction of the vector and curl your fingers, that is the direction of the applied torque. In this example, the area of A to B is equal to the area of B to C, 2 inches squared. Modulus elasticity is 29,000 KSI for steel. And the goal is to find the torsional reactions at each end and the torque in each segment. And so here's more of an isometric view of the same setup. Again, it looks like a dumbbell, but this collar here represents attachment to a solid support. So this thing is fixed at A, fixed at C. It is 6 inches and 18 inches, and there's your 50 kip inch vector. Like I said, if you follow the right-hand rule, curl your fingers, that's what you get. So when a torque is applied, you get a resulting twist is induced. Anytime you torque something, you're going to get a twist. So here's the grid system of this rod before we put the torque, and see how it torqued when you put the torque on it, you can see how it twisted at the most right there at B, and it twisted nothing at A and C where it's fixed. And let's see if I go back and forward. Okay, so you see how it's twisting right there in the middle? So the twist, phi, is maximum at the location of the applied torque and is 0 at the points of support, like I mentioned. If we look at segments A, B, and BC independently, each segment must have the same twist at B because of compatibility. You can't have something different happening on one side than the other side if it's all rigidly attached together. So we can, in our minds, we can virtually separate the two rods and look at the twist at B on segment AB, or look at the twist at B on segment BC, and they will be equal to each other. So we start by making two cuts and solving for the internal torques. Cut number 1 is a cut somewhere between A and B. Cut number 2 is somewhere between B and C. Okay, so for cut number 1, and here's my free body diagram, by the way. I do not know the reaction at A. I do not know the reaction at C, but when I don't know what the reactions are, I draw them in the positive sense. So again, using the right-hand rule, running my thumb down from B to C, curling my fingers, RTA, I drew it as positive. RTC, I drew it as positive. If we make a cut somewhere between A and B, then this is my free body diagram of the segment. And I have a RTA, an unknown reaction, and I have an unknown internal force here at AB. So summing my moments equal to 0. Both of them are drawn in a positive sense. So RTA plus TAB equals 0. That therefore TAB, the internal torque AB, is equal to the negative of the reaction at TA. And that's really all I can get from cut number 1. Cut number 2 is somewhere between B and C. And this is a free body diagram of cut number 2. And if I sum the moments, I have my unknown reaction at A plus 50 kips plus my torque and internal torque at BC, all drawn in a positive sense. So TAB plus 50 kip inch plus TBC equals 0. See here I substituted for RTA minus TAB. Therefore, TAB minus TBC is equal to 50 kip inches. So the internal torque in AB minus the internal torque from B to C is equal to my applied torque, 50 kip inch. Is everybody following along? Any questions so far?
Professor, I got a question.
Sure.
Why is the T, so T is the internal and R is the external?
Yes, that, and different authors, different instructors may use different variables. There's a myriad different ways to label your variables. But what I'm trying to do to be consistent is anything that is a external reaction is an R, and anything that's an internal force, I labeled with the T.
Okay.
Does that make sense?
Yeah, and then why is our, can you explain why is our T negative if they're both twisting the same way or rotating the same way?
Yes. So you're talking about right here?
Yeah, because you know right here in the, when you did the equation over here under cut 2, it says negative TAB plus 50.
Yes.
Right there.
Okay, well, start with your free body diagram here. And you see the red cut surface? Stick your thumb out away from that cut surface and curl your fingers. and you'll see that both RTA and TAB, the way that they're drawn, are both positive.
Mm-hmm.
So RTA plus TAB is equal to 0. They're both positive. So what that means is TAB is the negative of RTA.
Oh, okay.
Okay, so now I go down here and I draw the same thing. RTA is drawn positive, you know, again, with your thumb going away from the cut surface. RTA is positive. The 50 kip inch is positive, and the internal torque from B to C is drawn as positive. So all three are positive. So that's why all three here are positive. But I already found that RTA is equal to minus TAB right here. So I substituted that in.
Got it.
Okay. So that's my conclusion here is TAB minus TBC is equal to 50 kip inches.
Got it.
Okay. Any other questions at this point? Okay. All right. So now we need to equate the twist at B due to torque AB and the twist at B due to the torque BC. Remember, the twist due to the torque along this has got to be equal to the twist due to the torque along this side, because the twist in the middle at B here is the same twist. Okay, so twist, and we did this last time, twist is defined as the sum of the segments, but the basic equation is TL over JG. So in order to use this, I need to know what my polar moment of inertia is. JAB is equal to pi over 2 C to the 4th. And this was a 2-inch diameter rod. So C is 1 inch. So J is 1.571 inches to the 4th. And JBC is the same rod. So JBC also equals 1.571 inches to the 4th. G for AB, the problem was defined as steel. So G from your textbook is 11,000 KSI. Get that on your back cover. And G for BC is the same material. So it's also equal to 11,000 KSI. Therefore, the twist at B due to the torque AB is equal to twist at AB is equal to the torque AB, LAB, JAB, GAB, and I can fill in all my numbers. AB is 6 inches long, and we just found J and G. So the twist at B from the torque at AB is TAB over 2880.2 kip inch. That's just a summation of all this stuff. So really, this is just like what we did on the axially loaded members. We have a proportionality. So the torque is proportional to the twist, or the twist is proportional to the torque. The twist from B to C is the torque from B to C, LBC, JBC, GBC. So I plug in these numbers. Segment BC is 18 inches long and has the same J and G. So the twist at BC is equal to the torque BC over 960.1 kip inch. Since phi BC is negative by the right-hand rule, in other words, if I take my thumb at BC and stick my thumb out from the cut surface and curl my fingers, then it twisting this way is negative. So the twist at AB, again, stick my thumb out from the cut surface, curl my fingers, the twist from AB is positive, but the twist from BC is negative. So twist AB is equal to the negative of the twist BC. Okay, does that make sense to everybody?
Yep.
Okay, good. So therefore, here's the big substitution. Phi AB is equal to TAB over 2800. So that goes here. And phi BC is equal to TBC over 960. So that goes here with the negative sign. Now I've got this relationship between these two. And the torque in AB is equal to -3 times the torque of BC. That's just this over that. Anyway, simplifying this, I get that TAB is equal to -3 times the torque of BC. Okay, now we can substitute. Remember a minute ago on the previous slide, we solved that TAB minus TBC is equal to 50 kip inch. Well, I can substitute this in. So -3 TBC for the TAB minus TBC equals 50 kip inch. So TBC is equal to minus 12.5 kip inch, just straight up substitution. Now that I have that, I can plug that back in here, solve for TAB. TAB is 37.5 kip inches. So the induced torque on AB is positive and the torque on BC is negative. Now we can draw a torque diagram. We talked about actually loaded diagrams and we talked about a torque diagram. I feel it's very important that you're able to draw an axial load diagram or a torque diagram so that you can see what's really happening internally on these things. So if I draw the torque diagram, the torque from A to B we just solved is 37.5 kip inch. And we know it's constant because there's no other applied loads in between these 2 points. And we solved for the torque from B to C is minus 12.5 kip inch. And we know that that's constant. If there was another torque applied somewhere between B and C, how would we handle that?
You'd have to make a third cut.
Exactly. Thank you. You would make a third cut and you would solve for the third unknown, T, whatever that would be. But yes, that's how you would solve it. Do another cut and you'd have to sum all the pieces together. With the internal torque diagram, we can now calculate the twist at B. And I say we can now calculate the twist at B because we can look at the diagram and say, oh, from A to B is a constant 37.5 kip inch. And from B to C is a constant minus 12.5 kip inch. So we can visually confirm what the torque is over each of these segments. So the twist from A to B is equal to the torque AB, LAB, JAB, GAB. I now have all the pieces. Positive 37.5 times 6 inches over 1.571 over 11,000. And that gives me 0.01302 radians of twist. And if I go back here for a second, okay, so that is the magnitude of this twist right there. And it is positive by the right-hand rule. Right there. Okay. Now, remembering that the phi is equal to the sum of the TL over JGs of each segment, that equation gives you a relative twist from one point to another point. So we can calculate the twist at C by using this equation. The twist at C, or the twist from A to C, is equal to the twist from A to B plus the twist from B to C. That's the sum right there. The twist at A is equal to 0 because it's fixed. So if I sum the twist from A to B, this segment, plus this twist from B to C, this segment, then from A to B, I already know is 0.1302. And then I put in what I know for B to C, minus 12.5 kip inch times 18 over 1.571 inches to the fourth over 11,000. And I get 0.00000 radians, which is what it should be because at point C, it's fixed. Okay. Go back here to illustrate that point. So if I want the twist at B, the twist at B is found from the equation TL over JG, but it's a relative. So if I find over segment AB, it's only because at A here, there's 0 twist. So that means the twist that I find from this equation is the total twist at B. If I apply the equation here, then if I used phi BC is equal to just the torque BC, LBC, JBC, GBC, what number would I get? I would get minus 0.03, whatever that number was. Why would I get that number? Because that number would be the twist relative to B. Is this making sense?
Yes.
Is it negative also because of the right-hand rule? Is that the point that you're making?
It's negative because of the right-hand rule, but the point that I'm making is that this equation right here, phi is equal to twist is equal to the torque times L over JG is a relative twist. So from 0 to here gives you the twist at B. But from here, which is not 0, to here is a relative twist of minus 0.132, whatever that was. But when I did the twist from A to C, the twist at A is 0. And when I added it all up from A to B to C, I got 0. The relative twist at C relative to A is 0.
Okay. Thank you.
If both sides are fixed, does that mean that the twist of one is always going to be equal to the opposite of the other if it's fixed?
A is fixed, C is fixed.
Yeah, so when both sides are fixed, will the twist from one cut be the same as the opposite of the twist of the other cut? Always?
Yes, always. Yeah, I could have made this cut anywhere along here. And where I cut it at B just happened to be the maximum twist. But if I cut it over here, you see that there's somewhat of a less than maximum twist. But if I had added up A to B, which was positive, and then I added a little bit of segment here, which is negative, that total would be the relative twist here from A. And if I had done the exact same thing from here to C, it would have been the negative of the same answer. So yes. However far you twisted from A, you have to get back to 0 at C because A and C are both equal to 0. Okay, any other questions or should we move on?
One last question. So
Sure.
did you assume the direction of twist or was that a given?
The direction of the applied torque was given. I did not assume a direction of the twist, the direction of the twist was correct because of the positive or negative values of the torque in A and the torque in A to B and the torque from B to C. So this positive or negative and this positive or negative will give you the right direction on your twist. So now when I drew the diagram, clearly I had to pick a direction. So I drew it in the right direction, matching the applied torque. But the actual magnitude of the answer here, this answer is positive because this torque is positive. And that does follow the right-hand rule. Did that answer your question, or is it? Okay. All right, let's get to the flexibility method. So as you could see, the compatibility method was exactly the same as what we did in the actually loaded case. It's just that in the actually loaded case, we said the longitudinal deformation at B from AB has to be exactly equal to the longitudinal deformation at B due to BC. Well, this was twist instead of longitudinal deformation, but otherwise exactly the same thing. So is the flexibility method. It too will follow the same example. Okay, so I'm gonna, same parameters, same setup. However, the flexibility method is where we start by releasing the support at C, like so. So now this is my initial problem. My support at C is gone, and I want to find the twist due to my applied loading at C. So here's my undeformed, no, I'm sorry, this is deformed. This is my deformed bar. So it twisted, and you can see that it warped to the point of the torque. And then from that point on, it's basically a straight. And this portion here is twisted, but it's not warped. It can't be warped because there's no other applied torques out here. So this portion is unwarped, but the whole thing is twisted. Okay, so we're going to start by finding our reaction at A. Here's my free body diagram. I have no other forces on here because we released our support at C. So I have an unknown reaction at A, and I have my applied torque at B. Sum the moments. I have my reaction, and again, draw everything according to the right-hand rule. So my reaction is positive, my applied torque is positive, so my reaction at A has to be minus 50 kipinch, just by summing the moments. And always, for reactions, you always got to put a direction arrow. Because this is negative, my assumed direction was incorrect. It is the opposite direction. So you indicate that with your directional arrow. Now we need to create a torque diagram by creating two cuts. See, now I've drawn my reaction the way that it is. Cut number 1 is between A and B, and cut number 2 is between B and C. For cut number 1, do a free body diagram. I have an unknown internal torque, AB, according to the right-hand rule, and I have my reaction. Sum the moments, and TAB is equal to a positive 50 kipinches. So the internal torque from A to B is positive 50 kipinch. Okay, I took cut 1 and 2 and kind of shoved them up here so that we can do cut number 2 down here. Cut number 2 is through this region. And here's my free body diagram with my unknown torque, internal torque from B to C. Sum my moments. I have minus 50 plus 50 plus TBC equals 0. TBC is equal to 0 kip inches. So now I can draw my torque diagram. I found from A to B, positive 50. I found from B to C, 0. So this is my torque diagram.
Sorry, Professor, can you go back just a little bit?
Sure.
Just one slide.
There.
Yes. Thank
Let me know when you're good.
Okay, thank you.
Okay. So there's the torque diagram. Now, the twist is equal to the sum of the segments, the torque, the length, J and G for each segment. J, again, is pi over 2 times 1 to the 4th, 1.571 inches to the 4th, which is equal to JBC. And GAB is 11,000 KSI, same as GBC, just like the last example. So the twist from A to C, is equal to the segment AB plus the segment BC. The torque in segment AB is 50 kip inch times 6 inches over 1.571 over 11,000 KSI. The torque in segment BC, as you can see from the torque diagram, is equal to 0. So my total twist is a positive 0.01736 radians. Now we need to do a restoring torque. We need to find the torque applied at C that restores the twist at C back to 0 radians. Because after all, C is fixed. So it needs to be squeezed or twisted back to the 0 point to restore it to its original condition. So we're going to solve for this restoring force. So T is for torque, R is for restoring at C. So TRC is the restoring torque, and we're going to solve for it by equating it to the radian twist that we got from A to C. So the restoring torque at C is equal to phi AC, basically just solving this equation here, phi AC, JAC, GAC over LAC, which is the minus. And see, why is it minus? Use the right-hand rule. The right-hand rule, if I stick my thumb out from the face of the cut and curl my fingers in the positive direction, the rotation, the twist to get back to 0 is the opposite. So that has to be a minus 0.01736 radians to bring it back to 0. 1.571, 11,000, and the total length from A to C is 24 inches. So the restoring torque is minus 12.5 kip inches. Any questions so far? Okay. So the torque diagram for the restoring force from A to C is minus 12.5 kip inches.
Professor?
Yeah.
So what about if you have like different radius between from A to B than from B to C? How you gonna like use it? Because here, like you took the sum of the length.
Uh-huh.
Because you have like the same radius you work with it, right?
Right. Uh-huh.
You have different like radius.
That's a good question. I hadn't thought about that. So your torque here, you can put in your different materials here and here, right? So what you're saying is, what if one rod was 11,000 and the other rod is 20,000? Or one rod is 1.571, the other rod is 3, something different. So this equation, you can see how these don't make any difference at all. And you'd still have that same radian rotation here. Now you come down here, and what you would do is in this equation here, you have TRC times LAB, JAB, GAB plus TRC, LBC, JBC, GBC. So you have the two pieces. And then what you do is you just factor TRC out and then solve for TRC. So yeah, that's a great question. Yeah, I haven't thought about that, but that's how you would do that. Because the torque is still going to be constant, but the properties don't necessarily need to be constant. Did I answer your question, or did you have a?
Yes, of course. Thank you.
Okay. Okay. So we've got our released torque diagram. We have our restoring force torque diagram. Now all that is left is to combine them. And so when you combine this with this, you get this torque diagram. 50 minus 12.5 is 37.5. 0 minus 12.5 is minus 12.5. So this is my final answer. This is my final torque diagram. Thus, TAB is 37.5 kip inch. TBC is minus 12.5 kip inch. And box your answers. Okay, so that was it for indeterminate torque structures. Any questions? Okay. Which one you want to use is exactly the same, not argument, debate that we had for actually loaded members. It's your preference. Whichever one makes sense to you, that would be the one to use.
Professor,
Yes.
I thought we got 50 kip inches for the first diagram.
We did.
So where did the 37 point whatever come from?
Okay, the first part of this was that we released C. Okay, remember this is a two-part problem. And we solved it by first we released C and we found what the torques were in that condition with no support at C. And so we went through all this math to determine that if I release C, I have 50 kip inches from A to B, and I have 0 kip inches from B to C. But that doesn't really happen. C is not released. C is fixed. The problem is fixed at A, fixed at C. So that's not reality. That's just like a virtual way to look at it. So this 50 kips and 0 kips is not real. It's just from the load effect. And then what we did is we went down here and we found a restoring force. Well, this restoring force also is not real because there's no load here, if you notice. All I have is a restoring force without the load on it. And I found what the torque diagram looked like with doing the math just from the restoring force. Do you see what I'm doing here? I broke a complicated problem up into 2 bite-sized pieces. One, I solved for the load with no support at C, and then I solved for a restoring force at C with no load. But the final answer is you have to combine the two together. So the answer with no support at C is not the right answer. The restoring force with no load is not the right answer. But when you add the two pieces back together, you get the right answer.
Okay, that makes sense. Thank you.
Okay, no problem. Any other questions? Don't be shy. It's now's your time. All right. Well, if anybody thinks of anything, just give me a holler. I think we're probably gonna have plenty of time at the end of this. I think this is gonna be so much shorter because the last topic that I have is power transmission. And I think I gave or will give one homework problem on power transmission. So here's the deal with power transmission. When you use a circular shaft to transmit power, like a drive shaft on your car, they are sized to resist a torque that is based on both the power and the angular speed of the shaft. So if you had a motor, and a motor is rated at a certain power, it could be electrical, it could be diesel, it could be gas, whatever. But if you had a motor rated at such a certain power, then the size of the shaft or the size of really the torque that is generated is a function of both the power and the speed of revolution of the motor or the drive shaft. Okay, so you could have a lot of power, and if the revolution of the drive shaft is slow, you're going to have a huge torque. But if you have a very high RPM, then you have a much smaller torque for the same power. Is this making sense to anybody?
Yes.
Yeah.
So I guess one way to think about it is you're driving home. You're driving home because you're all at Cal Poly, in your classroom. So, after the class, you're gonna go back to the parking garage, get in your cars and drive home. And somewhere in Pomona, before you get on the freeway, you're stopped at a light. And when the light turns green, you notice that a big rig tractor truck and a motorcycle both pull away from the light together. And the motorcycle, the guy's screaming that thing at 12,000 RPMs on that motorcycle. And the big rig truck is pulling away at like, I don't know, 800 RPMs, 1,000 RPMs. So what is the analogy? A motorcycle is something that can produce a lot of power. Those things really are amazing, how much power they can get out of such a teeny weeny little motor, but they are at very high RPMs. So what does that mean? That means the torque is really low for that given power. A big rig truck tractor, on the other hand, is built for exactly the opposite reason. It is built to generate tremendous amounts of torque to get a very large mass rolling. And so the power is reasonable. I mean, those big rigs are putting out like 300, 400 horsepower, but the torque is unbelievable, like 1,800 to 2,400 foot-pounds of torque, compared to the motorcycle is probably putting out 50 foot-pounds of torque. Does that make sense? You guys see the relationship between RPMs, torque, and horsepower?
Yeah.
Okay. So power is defined as work per unit time. We talked about this a bit ago. So power is work over time. Work is defined for torsion. In the torsional case, work is defined as a torque times an angle of rotation. So work is always a force through a distance. In this case, it's a torque times a twist. Therefore, if during a differential amount of time, dt, a shaft rotates a d theta due to an applied torque T, then the power is equal to the torque times the differential rotation over the differential time. If we use angular velocity, omega is equal to a d theta over dt, or a differential twist over time, then power is equal to torque times omega. In the SI system units, power is equal to watts, where 1 watt is equal to 1 Newton meter per second. In the US customary system, power is generally referred to as horsepower, where 1 horsepower is equal to 550 foot-pounds per second. Power can also be defined in terms of frequency, where F is frequency is measured in hertz, and a hertz is a cycle per second. So you could do it either way. In other words, power could be torque times omega, or power can be 2 pi times the frequency times torque. Either way is equivalent. Okay, so you ready for an example? A torquey example?
Yeah.
All right, that was good enthusiasm. The USS Iowa is a 1943 World War II era battleship. Has anybody gone down to the port of Los Angeles and visited the USS Iowa? Oh, somebody, okay, great. I've been there a couple times, and it's interesting when you take the tour and you get to walk all over it and see the guns and see the engines and all that good stuff. So it's really interesting. So there's the USS Iowa doing training rounds, clearly. All right, so this ship, built in 1943, was fitted with a total of 212,000 horsepower. Pretty good. That's a little bit more than my motorcycle. And all that power was distributed to 4 drive shafts or 4 propellers. Each shaft was 24 3/8 inch in diameter and typically would spin at about 200 RPMs at top speed, which is pretty crazy when you think about how big those propellers are. So, given all this circumstances, determine what the induced shear stress is in the drive shaft at full steam. So there's the boat. I believe this photo was taken in 1985. This is the USS Iowa, and these are the propellers that I'm talking about. And those drive shafts would go from the end of propeller through this fin here up into the body of the ship and would connect to the boilers and engines and turbofans and all that good stuff. So some way you had to transmit the power generated inside the belly of the beast to the propellers. It was those drive shafts. All right, so solution. The power was distributed to 4 shafts. So the power per shaft is P equals 212,000 horsepower over 4, or 53,000 horsepower per propeller. And if I convert that, then 53,000 horsepower times 550 foot-pounds per second per horsepower gives you something like 29,150,000 foot-pounds per second. Omega was 200 revolutions per minute times 2 pi radians per revolution times 1 minute is 60 seconds, and that gives you 20.94 radians per second. So the power is equal to the torque times omega. So the torque is equal to power divided by omega, or 29,150,000 foot-pounds per second over 20.94 radians per second gives you 1,392,070 foot-pounds of torque. Let that settle in for a second. 1,392,000 foot-pounds of torque. Do you know what you tighten your lug nuts to? It's something like 120 inch-pounds. This is unbelievable amounts of torque. Or I can say that is 16,705,000 rounding up inch-pounds. That's the applied torque. So if the shaft was 24 3/8 inches, then C is equal to that over 2, which is 12.188 inches. So my polar moment of inertia is pi over 2 C to the 4th, which is 34,662 inches to the 4th. Now my torsional equation that we did last time, my torsional stress tau is equal to the torque times the radius over J. So I have my, and I'm going to say that all over again, 16 million and something inch-pounds times 12.188 inches over 34,662 inches to the 4th gives me a grand total of 5,874 PSI. That is my induced shear stress at full steam. And of course, we box our answers. So this seems pretty conservative to me. I'm sure that those drive shafts were made out of some sort of a steel that can probably tolerate shear stresses somewhere in the 20 KSI range at least. So I think they built in a lot of factor of safety. I mean, after all, this is a warship that's going to be shot at. So you don't want your drive shafts breaking because you got too crazy with them. But anyway, that's an example of the application of a little power. Any questions?
Professor, wasn't our T a different value?
So T, I converted it. T was 1,392,000 foot-pounds, and I converted it to 16,705,000 inch-pounds.
Oh, okay. I missed that. Thank you.
Yep, no problem. Make sure I put it there. Yeah, 16,705,000 inch-pounds. Yep. So if you tour, I know, going off on a tangent, but if you tour the USS Iowa and you happen to do it on your birthday, so your wife or husband buys you the special all access pass, then you get to go down there and you get to see where the boilers are. And then you see where all the steam goes from the boilers into the turbos, not turbos, but turbofans. And the turbofans take the steam power and spin it like a turbofan. And that spinning goes through a whole bunch of gear reductions. That's actually attached to the drive shaft, and it spins the drive shaft. And so even though this doesn't seem like a lot of stress, under this amount of torque, they told us that that whole drive shaft rotates like 360 degrees before the propeller actually starts turning, because the length of that drive shaft is like 100 and something feet long. It's so long that even at 24 inches in diameter, it does one full rotation before it starts turning the propeller. So anyway, I thought that was kind of interesting stuff. All right, we still got 20 minutes, so if anybody has any questions.
Not very mechanics related, but how much did the tour cost?
Well, this was all before COVID. So I think the basic tour was like 30 something dollars. And then my wife did get me the all access pass. I think that was like another 40 or $50, something like that. But it's, I don't know. I thought it was worth it because the basic tour is like an hour to 2 hours. You go as fast as you want. And then the extra was another 2 hours. So I was on the boat for like 4 hours. We saw so much stuff. It was pretty neat. Nicholas asked, so the 5874 is a shear stress. Yes, that is absolutely right. Torsion produces shear stress. Yep. Okay. Leilani, some students are curious when the midterm grades would be curved. It is at the end of the semester. Yes, it is. So I have a curving algorithm that I've been using for many, many years now. But one of the variables that goes into the curving algorithm is where the final scores are. So where the final scores, I have an idea where the average student should be. And so that number feeds back into the curve. And the midterm, first midterm, second midterm, and final are all curved independently, but I don't know what that curve is until I'm finished grading the final and get down to the end. So that's why I can't give people exact numbers of where they are. But if you're curious about where you are, I can tell you where you are without the curve, and then you know that you're going to be better than that. But not, how much better, I don't know yet. We covered today 5.3, I think, is power, and 5.5 is statically indeterminate. So yeah, 5.3 is power and 5.5 is statically indeterminate loaded members. Yep. Okay, any other questions? If and when you guys take dynamics, make sure you tell your dynamics teacher to use the USS Iowa as some kind of an example where they can do projectiles from a 16-inch gun or something like that. Was somebody about to ask a question? I rudely interrupted.
Next chapters we're going to cover are chapter 6.
Yes,
Oh,
sir.
okay.
Yes. Good question. Great question. We are going to dive right into chapter 6 starting on Thursday. All right. Not hearing any other questions. Hope everybody has a wonderful evening, and we will see you on Thursday.
Thank you,
you.
Professor.